Welcome back to my channel. My name is Dr. Arzu Jabra. I have a PhD in organic chemistry, and I am an organic chemistry tutor. I tutor organic chemistry for MCAT as well. And I'm also an academic mindset coach for college students. And what that really means is that I help students who are overwhelmed because of college or because of MCAT feel a lot more in control of their time and energy, and actually feel really excited about the whole process of going to graduate school or getting a professional degrees. So for today, we are working on solving MCAT Kaplan problems. So today we are actually going to be solving the carboxylic acid derivatives problems from Kaplan, and let's get started. All right, so we are here. All right, so the first problem is what would be the product of the reaction above? And so when we look at the reaction over here, right, this is a carboxylic acid, and we are reacting that with sulfonyl chloride, right, SOCl2. So now the product of this reaction actually is sulfonyl, or actually carbonyl chloride, because what we do know is that SOCl2 always converts, right? It will convert your OH to a Cl group. So it always just converts an alcohol to a chlorine. That's what's happening over here. Okay, so then actually option D is the correct answer. Don't get confused with option A, because in option A, they're only switching the hydrogen with the Cl, right? But that's not true, because the entire OH converts to a Cl in the transformation. Okay, during hydrolysis of an acid chloride, pyridine is actually added to the reaction vessel, and this is done because. So if you think about reaction of an acid chloride, which is effectively this, so a pyridine, or which is actually a base, is added to the reaction vessel, like almost as like a second reactant, as a reagent in the reaction, right? And why do they actually do it, right? Because when they do the hydrolysis of this reaction, meaning they actually react that with water, right? And hydrogen chloride is actually the side product of the reaction, which is an acid. So when acid is formed, which actually is the side product of the reaction, what you really want to think about is you don't want to have an acidified solution, right? So then they actually add the base to neutralize the reaction. And to neutralize the reaction. And also, if we actually think about it, right, the carboxylic acid can very quickly react with HCl, right? Because it'll get protonated over here, and there's a possibility of a reverse reaction that can actually happen. If HCl was the side product of the reaction, right, then the Cl minus will just attack here. I mean, it can actually form water as well. So then water would just be the side product, the acid chloride would just be the side product of the reaction. And to avoid the reversibility of the reaction, they add the pyridine. So HCl can be neutralized, and the reaction no longer is just, what is it called, like irreversible reaction. So it can actually become an irreversible reaction. And so option C, hydrolysis of the reaction leads to the formation of HCl, is the correct answer. And then we're trying to basically neutralize HCl, right? So option C is the correct answer for this problem. Okay, the next problem is what would be the primary product of the above reaction? So this reaction is the reaction of an alcohol, right, with an acyl chloride. And if you really think about it, the reaction of an alcohol with an acyl chloride, what we are really seeing here is that we have the lone pair of electrons on alcohol. And so the lone pair of electrons on alcohol can attack over here at the carbonyl electrophilic carbon, and it can undergo a nucleophilic substitution reaction and kick out a chlorine, right? So, or nucleophilic addition reaction. So, but here the thing really is that there are two different types of alcohols that are reacting in the reaction. If we think about option A, the secondary alcohol, right? The 2-degree alcohol is forming the ester over here, and the primary is just untouched, which does not make sense because we do see that there's more steric hindrance at the secondary carbon. There's less steric hindrance at the primary. And if we were to choose one of those two, then the primary should actually go first instead of secondary, right? If you look at option B, then this is secondary. Secondary is reacting actually over, sorry, this is primary, and primary is reacting over secondary, which does make sense, which does give us an idea that, okay, yeah, that is a more reasonable product. For option C, okay, they are not really making an ester, so that's a problem. They're just making a ketone. That's an incorrect reaction. For option D, they're really reacting with both. So because the reaction is basically testing you on the selectivity of which of these alcohols actually is reacting, unless they said excess of this reagent, I'm going to assume 1 mole of acyl chloride was actually used. Therefore, a primary alcohol, which is actually less hindered alcohol compared to a secondary one, would be the one favoring the reaction, would be the one participating in the reaction. And then that's why actually option B is the correct answer for this problem. Okay. Next question. To produce the primary amide, an acid chloride should be treated with, right? It's a really good question. When I was actually going through these problems, it tricked me for a second, right? So watch out for not getting tricked in the problem, because even though it's like a really simple problem, the wording can just like trick you. So to produce primary amide, right? We are forming primary amide. What does that mean? So we are starting off with acid chloride. Okay, and on the acid chloride, you're reacting that with primary amide. This is the primary amide. Okay, so if you should treat the reactant with what to form a primary amide? Okay, so to produce a primary amide, a primary amide is an amide, right, which is actually connected to 1 carbon. So a nitrogen over here is actually connected to 1 carbon, which is the primary amide. And so we already have 1 carbon connectivity. So then all we actually need for this reaction is actually just ammonia, right? When I was actually going through these problems, I thought, oh, I would definitely reacted with the primary amine, right? And well, tertiary amine is really off the charts, and alcohol is really off the charts because that's not really giving us the products actually we want. But let's think about primary amine though, right? RNH2 is a primary amine. If you actually do react that with the primary amine, you would actually form a secondary amine over here, right? Because now this nitrogen is actually connected to 2 carbon chains, 1 over here and 1 over here. So now that is a secondary amide, actually, sorry, not amine, secondary amide. And that's why a primary amine would be formed, an amide would be formed only by ammonium. Okay, next problem. Which of the following would be the best method of producing methyl propanoate? Okay, so first things first, let's draw out what methyl propanoate is. So 1, 2, 3, propanoate, 1, 2, 3, 1, 2, 3, propanoate, and then double bond O at the 3rd carbon because we have a we have this, right? So this actually is a methyl, right? Methyl propanoate. This is the propanoate. So how would we prepare that? Reacting propanoic acid and methanol in the presence of mineral acid. So propanoic acid, 1, 2, 3, is this, plus methanol, MEOH. In the presence of mineral acid, let's say H2SO4 is a mineral acid in the presence of H plus. So if we think about the product, we are actually making this compound. So it is forming that. In the second option, we have propanoid chloride, which means kind of like this, right? And then reacting in the presence of a base with what? Ethanol, okay? That wouldn't make a methyl ester. If you react that with an ethanol, we're not going to get a methyl ester. We're actually going to get an ethyl ester, and that's why option B is not the correct answer. For option C, reacting propanoid chloride with aqueous base. So if you have propanoid chloride, you react that with the base, you will just form carboxylic acid, right? That's just hydrolysis of carboxylic acid. So then you're just going to form this reactant, reacting propanoic acid with ethanol in the presence of mineral acid, reacting propanoic acid. Again, we are again just forming ethanol or the ethyl ester, not the methyl ester. And that's why option A is the correct answer for this problem. Okay. Next question. Which would be the products of the above reaction? So we have an anhydride here, right? And over an anhydride, we are reacting that with ammonia. So what would be the product of the above reaction? We know how this reaction works. The lone pair of electrons would go over here. So that would just give us CO minus, right? And then so the tetrahedral intermediate, and when the tetrahedral intermediate breaks open, right? So when this oxygen of O minus comes back down, these electrons, the bond breaks, and again, we are trying to form a bond. When you're trying to form a bond, you'll have to break a bond, right? You're forming a bond, so we have to break a bond. So over here, then we would actually have to we would break that lone pair of electron, or we would break that bond to actually have our lone pair of electron ending up on the oxygen. So now one of the product is an amide. The other product actually just is a carboxylate, or this is a anion of carboxylic acid, right? And that answer is option D. So that's why it is just like the correct answer. And then to neutralize it, because it's a negative charge, it would be neutralized with a ammonium cation, right? And yeah, because first off, we would have NH3 here, right, with a positive charge, and then NH3 ammonia will come in as a Bronsted base. We'll grab, or we can even think of that as like a Lewis base. We'll grab the hydrogen, make the product neutral, and so NH4 plus is then one of the side products of the reaction that will sit here as a counter ion for that negative charge. So option D is the correct answer. None of the other answers actually make sense. So moving on. Which of the following correctly shows the intermediates and products of the above reactions? So the first product of the reaction is pretty simple. We have already seen it. The first answer is Cl, right, where the OH is replaced by chlorine. In the second step, we have ammonia. So in the second step, we have C double bond O and NH2, right? We know the chlorine is a really good leaving group, so it will be replaced by NH2. Next is hydrolysis, base catalyzed hydrolysis of amide, and we know what that also forms is the NH2 is replaced by NOH. So then that is the product of the reaction. If you look at the sequence of answers, the answers are really hilarious. Like they did the chlorination of this carbon over here, which makes no sense. right? It's not even at the alpha carbon. Okay. Anyways, so option C, I see here, okay, is the correct answer. And I really like the option C and option D because they're very similar, and they want you to find out which is the exactly correct answer. If you really think about it, for option C, right? The third one, there is a negative charge over here. And for the third one over here, there is a carboxylic acid. So if we really think about, should we actually have a negative charge, or should we just have a carboxylic acid? Let's look at the reaction conditions. We have a ton of base, right? So an acid in the presence of base can never just be an acid, right? It will actually be a deprotonated acid because if it is sitting with a base, if we have NaOH. So actually, it will prefer to sit as a negative charge in a basic reaction conditions. And if we do the workup in the last step, we can neutralize it. But if the reaction conditions are basic, we would first form the anion of the acid, right? And then scientists can obviously, when they're working on it, to get the neutral product, they can add a little bit of acid in the workup step. But they haven't really talked about the workup. So actually, option C is the correct answer over here. All right. Which conversion between carboxylic acid derivatives is not possible by a nucleophilic reaction? Okay, so what we are really seeing here is that reaction of an acid chloride converted to an ester. Is that possible, right? Acid chloride to an ester? Yes, for sure. It's a possible conversion because we know that acid chloride, chlorine is a really good leaving group, right? It's a better leaving group than just OMe. And therefore, that conversion is possible. Acid chloride to anhydride. So acid chlorides are the most reactive derivatives of all the derivatives. Therefore, acid chloride can be converted to anything. Never question acid chloride's possibility of conversion, right? The next is anhydride to amide. If we actually look at anhydride, so there is a series of derivatives and the reactivity, right? So the order is acid chloride is the most reactive, followed by acid anhydride, followed by acid followed by an ester, not acid. It's followed by an ester, and that is then followed by amide. So this is also the order of reactivity. So you'll always see that acid chloride is the most reactive, followed by the reactivity of acid anhydride. And the reason is actually the leaving group abilities. When they have really good leaving group abilities, when the group can leave very well, it can react really fast. It can go and react to form anything else, right? So anhydride can also convert to amide because it is more reactive than an amide. And amide is actually the most stable bond, right? Because the proteins in our body have amide bonding, and amides are really strong, and that's why we're not melting right now, right? So that is like one of the strongest bonds. If you actually look at option D, ester to anhydride is a reverse order where we're going from less reactive to form something that's actually more reactive, and that's actually not stable. We always go from more reactive, right, to less reactive. Okay, so option D is the correct answer, that it is not possible by nucleophilic reaction. Okay, acyl halide make excellent reactant in carboxylic acid derivative syntheses because acid halides make acyl halide make excellent reactant because, okay, I already said, never question acid halide's ability to undergo transformation. Acid halide ions are really good leaving groups. There's a lack of rotation. That's not true. That is not why actually that they are excellent reactants. And then they're amenable to electrophilic attack. Halides are amenable to electrophilic attack. Also not really true. The carbonyl carbon is amenable to electrophilic attack. Halides are amenable to nucleophilic attack. That also halides are amenable to nucleophilic attack. That's also not true. All right. The last problem. Which of the following undergoes a Fischer esterification most rapidly? If you think about Fischer esterification, then a carboxylic acid reacts with a ethanol in the presence of H+, right? In the presence of a mineral acid to actually give us an ester. And that reaction is called a esterification, Fischer esterification. So now if we actually think about it, we are really reacting after activation of carbonyl, we're actually reacting the alcohol with what at the carbonyl carbon, which really means that if the carbon is more deficient, right? If this carbon is more electron deficient, this reaction will go faster if this carbon is electron deficient. So why are we really thinking about that, right? And the reason is that if you think about this carbon and all these different carbons, they differ in the number of carbons attached to it, which means they differ in the electronics and sterics as well, for sure. But let's talk about electronics. Let's see how adding more carbons, meaning adding more electronics, does that actually help the electron deficiency of that carbon? It actually does not, because then these carbons are donating more electrons to the electron deficient carbon, and that will slow down the reaction because it's no longer that electron deficient, right? And then, so the more the number of carbons, the more reduction in electron deficiency. So same over here as well. There are 2 carbons, but over here, there is least number of carbons that are here for that are adding the number of electrons at the electron deficient carbonyl carbon. Also, here's the other thing too, that, right, the other thing is also that sterics too. So sterically is also favored, because then B, C, D would be sterically hindered when the alcohol is actually reacting here. So sterics and electronics both favor option A as the correct answer for this problem. And so A will undergo the reaction most rapidly or the fastest. So that these were all the problems. And next time I'll be bringing more problems from the next chapter, which actually is the amines, the chapter amines, right? So that's what we'll be working on next time. And so we're getting closer towards the end of the sequence of Kaplan chapter problems. Very soon I'll start resolving like bigger practice problems, the chemistry sections, organic chemistry, and maybe chemistry sections as well. So watch out for that. And of course, if you need accountability partner, if you need technical knowledge help with chemistry, reach out to me on the link mentioned down below. And I think I mentioned this before. If you want to download these worksheets and practice them, if you don't have access to these problems, feel free to download the worksheet on the links mentioned down below. And until then, keep learning, keep growing, and I will see you guys next time. Bye now.